Okay, we have been working with the trajectory transfer problem, and last time we were solving one problem for the two asteroids which are moving in two different circular orbits, and then one satellite has to move from asteroid A to asteroid B and back from asteroid B to asteroid A. So, in that context, the part B of the problem we were continuing with. So, in the part B, we saw that this is asteroid A, okay, and the asteroid B is here in this place. So, initially there is some offset in the once the problem was that first the satellite has moved from asteroid A to asteroid B, and now again after certain wait period the satellite has to be returned from the asteroid B to asteroid A. Now, the wait period has to be such that the fuel should be minimized. Okay. It is a one possibility is that immediately the satellite can be launched and the asteroid A can be reached after some maneuver. So, that is always possible, but if the wait period has to be such that the fuel economy is to be minimized, then we need to apply the Hohmann transfer, because as we have seen that the R f, the final radius by the initial radius, in this case the earlier once the asteroid was going from the satellite was going from asteroid A to asteroid B. So, this was turning out to be less than 11.94, and therefore, the Hohmann transfer is the best possibility. So, once the asteroid the satellite from asteroid A, it moved to asteroid B. So, at that time the position of the asteroid A was given by A prime and the position of the asteroid B was given by B prime. So, the asteroid A was leading asteroid B by certain angle, which we showed to be 139 degree this we calculated to be 110 degree. Okay. So, delta theta as we can see, we calculated it to be 110 degree, which we have shown here in this place, and we have written here in this place also. So, now the problem starts with that a satellite has to be launched from B again, which should reach A with maximum fuel economy. So, then we started writing the equation and balance the angle first. So, delta theta B, which is the angle moved by the asteroid B before the satellite can be launched, it was written by delta theta B, this quantity. Okay. So, this is the angle before the satellite can be launched from the asteroid B. So, this is the position of the B, which has been written by B double prime. Now, the asteroid will be launched from the satellite will be launched from B. So, which is now at the B double prime position, and it should catch up the asteroid A, which is now at A prime, which is at the position A prime at the beginning of the motion from B prime. So, once the asteroid was at B prime, so at that time the asteroid A is at A prime, okay, and this is the position of B, and here this is position of A, and this is the gap delta theta, which we have earlier stated. Now, before the launch, asteroid B will move from this place to this place, which is given by B double prime. In the meanwhile, asteroid A prime, because it has the higher angular rate, so it will move from this place to maybe somewhere here, suppose, okay, or it may move to some other place depending on the angular rate and the radius of depending on the angular rate. and the time available. So, that time will be decided by how much time the asteroid B takes to go from this place to this place. Okay. So, obviously, if the satellite is to be launched from this position, okay, so by that time asteroid A must reach in this position, so that it can come and catch up here in this position. But because it is a moving faster, so therefore, it will go one round and it will come another round, then only it can be cached. So, that situation was described by this condition delta theta, which is the delta theta b, which is the distance moved by the asteroid B from here to here, plus 180 degree, which is the angle from here to here again, okay, and this must be equal to delta theta, which is the lead, initial lead, okay, plus delta theta a. This is the distance, this is the angle moved by A, okay, this is the angle moved by A, which will start from this position from A prime. So, it will start, it will pass over this place, it will go, and again once it will come here, then only it will be able to catch up this. Okay. So, this delta theta a, it will include the time for the passage of B from here to here, and then the passage of the satellite from this place to this place. So, whatever the time involved in this process is, the same time will be involved in delta theta a, and then we have subtracted minus 360 degree, because A is making one complete round, and therefore, this 360 should be subtracted, and we got this equation. Okay. Next, this is the final reduced equation. Next, we wrote the equation that delta theta a by W a, which is the time taken by A to move from this place, and it will come back and again it will come here. So, this is the angle delta theta a. It will start from here, pass over this place, come here, and again it will come here. So, that will constitute the angle delta theta a. So, delta theta a by omega a, which is the angular velocity of the asteroid A, this must be equal to delta theta b divided by omega b. So, this is the angle from delta theta b divided by omega b, which is the angular rate of the asteroid B. So, the time taken to cover this angle, and thereafter time taken to cover this angle from here to here. Okay. So, the satellite will move from this position to this position. So, how much time it is going to take? So, that time we are indicating as delta t 1 by 2. Okay. So, these quantities already we have computed delta theta b, we need to work it out. Okay. So, we have one relationship available, but this quantity is available to us. So, this is the half period of the satellite for moving in that elliptic orbit, and that is the same as earlier we have done. Either it goes from this place to this place, or either comes back from here to here, because the semi major axis is not going to vary. It will not differ either if it goes from here to here, or either if it comes from here to here, it is not going to change, and therefore, the time period, half time period or the full time period to go in this elliptic orbit, it will remain same. So, which has been added up here in this place. Okay. Now, we can insert this equation here in this place to work out for delta theta b. So, we can name this equation as say 1, and this equation, or maybe we will write this as p and this equation as q. So, inserting equation p, which is delta theta a equal to 7.501085 plus delta theta b, this is our equation p, into equation q, which we are writing as delta theta a divided by omega a equal to delta t 1 by 2. This is in So, the resulting equation after we insert it, so delta theta A we have 7.501085 plus delta theta B divided by omega A, this is equal to, and T half we have written as pi by mu under root times 2.75 to the power 3 by 2 times r to the power 3 by 2. And obviously, this quantity we have calculated it to be 71956,309 seconds. Okay. This we have done in the part A. Okay. Therefore, this is delta theta B here in this place. Now, we can write delta theta B by omega A minus delta theta B by omega B, this is equal to 71956,309 minus 7.501085 divided by omega A. Omega A is also known to us. Okay. Now, here what we can do, delta theta B we can take common and also omega B. So, this will make us, this will give us omega B by omega A minus 1. And omega A is the quantity which is known to us, which is 3 point, this was larger 7 point something, get back to this. Okay, so, omega A is 7.039390 into 10 to the power minus 8 radians per second. Okay. So, once we work it out, so this will turn out to be 71, this is 956,309. Okay, and after dividing this, once we compute this quantity, so this will turn out to be minus 0 point. So, here delta theta B and omega B, these are to be worked out. This is the quantity we are looking for. Okay, so, we need to compute this quantity and also we need to compute this quantity. So, 1 minus omega B by omega A, this will be 1 minus 3.0407308 into 10 to the power minus 8 divided by so this turns out to be 0.5680406. Therefore, delta theta B by omega B will be equal to delta T B, and this we can write as 1 by omega B by omega A minus 1 times 71956,309 minus 7.501085 divided by 393902 bracket closed. Okay, so, this quantity will obviously this is positive here. So, this quantity will turn out to be negative. So, we will see that this quantity will also turn out to be negative. So, after computing this, this will turn out to be around 6091540 seconds, and this is equivalent to 705.03943 days or 1.931649 years. So, this is what we wanted to compute, that how much will be the wait period, that is how much time it is going to take to move from the asteroid B is going to take to move from B prime to B double prime. So, that at this point we are launching. So, this is our wait period from here to here, or this you can say here this is the wait angle, writing in saying in terms of angles, and this can be converted into time like this. So, delta theta b, this angle divided by omega b, which is the angular rate of the asteroid B, okay, that gives you the wait period. So, finally, we have got the results which can be summarized as. So, part B is complete. So, summarizing the results, just the wait period before another launch from B can be done will be 6091540 seconds or 705.03943 days or 1.9349 years. So, what we have got time to travel in ellipse, this is 832.82765 days, and time to launch from A. So, this is the wait period. So, part A of the problem, part A of the problem. So, this is 390.8253 days, and third, now we have got time to launch from B, this is 705.03943 days. Now, once we have completed this, so whatever the work we have done till now, it is all about the transfer in the coplanar orbits. Okay. But if we see the work till now, it involves transfer from one orbit to other orbit. Now, if we consider that the transfer is to be done in the same orbit. Okay. So, if we have to do the transfer in the same orbit, then it is called the rendezvous problem. So, for the rendezvous problem, we have Rendezvous problem for two vehicles in same circular orbit. So, this is the last discussion for the coplanar last but one for the coplanar case. Next we will take in the circular orbit, here in the elliptical orbit. Right now we are considering the circular orbit, and therefore, thereafter we will go for the non coplanar maneuver. So, the non coplanar maneuver will be the last case to be considered. So, here in this case, suppose this is the orbit and we have two satellites here, satellite A and satellite B. Now, since both are moving in the same circular orbit, so in the same circular orbit we cannot catch it. Okay. The satellite A cannot catch satellite B, because if you try to thrust it, so its velocity will increase and it will go in the different orbit. So, what we need to do, that once the satellite this B is moving, this is already the gap, okay, the lead the B is having. So, once the satellite B moves from B to suppose another point which is C. Okay. So, whatever the time it takes to move from here to here, okay, in the same time A will move in a different orbit and it will go and catch this, like here in this place, and here given the O is the center of this circle. So, we join here in these two places and we will move B to little here in this place. Let us say that this is the position of the B. So, the satellite has to be, so satellite B will move from this position to this position. Now, this is the orbit in which we will send the satellite A. Okay. So, we can divide this angle, the whole angle, into two parts by using a bisector, okay, and this will give the, this point will be the perigee position of the satellite A while it is moving in this transfer orbit APC. Okay. So, APC, this is your transfer orbit. This is point B, this is your point B here. Let us name these angles. This angle is phi, this let us write as, this is a division, let us write this as phi, and angle from here to here this angle we write as phi AB. So, angle AOB, this is your phi AB, and angle BOC we will write as phi BC. So, angle BOC means angle from here to here. So, this is your phi BC. And angle AOP, this can be written as phi. Okay. So, we have to devise our plan how to work out this problem such that satellite A can catch satellite B while it reaches position C. So, the new position of the satellite B will be here in B prime, which is coinciding with C, and in the same place A is going to catch up. So, this we are showing this as the A prime also. So, we have vehicle B is leading vehicle A by an angle phi A B. Rendezvous is considered to be at point C. So, your orbit APC, the orbit APC is a faster orbit, because it is a covering larger angle in the same time as the the vehicle B or the satellite will be covering a smaller angle. So, therefore, we can write here as TAC for the transfer orbit equal to TBC for the circular orbit. Okay. This both time will be same. Now, TBC it is easy to write how much it will be. TBC circular this will be 2 pi by mu under root r to the power 3 by 2 times phi b c divided by 2 pi. So, you can see from this place that this is the time to cover the complete orbit, means 360 degree, and therefore, this has been divided by 2 pi, okay, in which is 360 degree converted to radians, and then multiplied by the angle phi b c. So, the phi b c is the angle from here to here. Okay. So, TBC gets reduced to, now instead of writing the full circular, we will just denote this with a subscript C to indicate it circular. Okay. So, TBC circular will become r to the power 3 by 2 times phi b c divided by mu under root, where r is the radius of the orbit, and mu as usual is the gravitational parameter of the heavenly body in consideration. Now, we need to work out TAC transfer. So, we will just indicate this with the subscript TR to be short. Okay. So, to determine TAC let OP show the bisecting bisecting line for angle AOC. Now, one modification we will do here. So, to make it different, so the angle AOP we have written as phi. So, we will write this as theta 0, okay, to make it different from the phi which is for AOB and BOC. Okay, so, it will make little distinction to this, and you can see that this angle theta 0. So, AOP which equal to theta 0, this can be written as phi AB plus phi BC divided by 2, okay, which is very clear, because this is the OP is the bisecting it, the angle AOC. So, AOC is nothing but phi AB plus phi BC. So, theta 0 known. So, the bisecting to determine TAC, let OP show the bisecting line for angle AOC. Let theta 0 position of OP with respect to OA. So, theta 0 we have written as phi AB plus phi BC divided by 2. Now, we have to find out how to, here two objectives are there. Now, you can look into this, if we can somehow or other calculate the eccentricity of this orbit. So, our case will get fairly convenient, okay, because here the at what time it is going to catch here, that is not known. So, if this angle is not known, at what angle it is going to catch. So, that is going to be decided by what will be the eccentricity of the transfer orbit, because depending on the eccentricity of the transfer orbit, the point C will be decided. So, what here we do that we assume the eccentricity of the orbit, transfer orbit. So, we will assume eccentricity of the transfer orbit, and then this case needs to be solved iteratively, because you are not going to get the solution in one shot. Here informations are not complete, and therefore, you assume the eccentricity, try to find out the time involved in the transfer. So, that the whatever the time B takes to reach C, and from A takes to reach to again C. So, these two times should match up. So, this has to be done by the iterative procedure. So, we assume the value of the eccentricity, calculate the time of transfer from here to here, and whatever the time of transfer from here to here is there, both of them should match. Okay. So, we list the steps to be worked out. Okay, so, here your angle is given. So, your TBC, calculate TBC, which is 2 pi by mu under root given phi b c. So, phi b c, this is known quantity. But going from this place to this place, this can be done in a number of ways. Either it is a possible that I go along this orbit rather than going through this path, okay. Or it may be possible that I throw it along this line and go along this line. But the thing is that if it is moving from here to here, if it goes in this orbit will be taking much more time, and therefore, it will not be able to reach in this place. So, maybe it passes over this place and comes again here in this place, then you go in a much larger orbit and then you are able to catch up in this place. So, those are discarded. So, these are the possibilities where these are the faster orbits, and you can come from this place and catch up here in this place. So, this angle is given to you, phi b c is given. This is the known quantity. So, once phi b c is known, then therefore, T b c can be calculated, and your T a c must be equal to T b c. This is the requirement. Okay. So, the second step is assume eccentricity for the transfer orbit. Okay. So, therefore, this becomes a trial procedure. Okay, or iterative method. Step 3 is for the assumed eccentricity and known theta 0. Theta 0 we are finding it from the phi a b and phi b c. Okay. So, for known theta 0, calculate T a c transfer. So, for known theta 0, we will just calculate it for the half of the angle. So, how much time it is going to take from half of the angle, and therefore, the time to go from A to B will be just double of that. Okay. So, the equations for the angular motion is known to us. Since the orbital angles are known, equation of motion is known. So, this is the equation of motion we will utilize. Integrate it between 0 to T 1 by 2 and 0 to theta 0. Okay. So, we can write from this place TAC transfer 2 times dt 0 to t 1 by 2, and so this will be 2 times r square d theta divided by h 0 to theta 0. Okay, r we can write in terms of semi-lattice rectum, and then in terms of eccentricity we can express it. Eccentricity we have already assumed. So, this becomes r equal to L by 1 plus e cos theta square. So, this will become L square divided by h, this h we are taking, and 1 plus e cos theta whole square d theta. H is nothing but mu times L under root. Okay. Here L is the zero to theta 0. So, this gets reduced to 2 times L to the power 3 by 2 by mu under root. Now, here onwards we have already solved this kind of case for Kepler's equation. So, we can apply the results obtained there. So, this we have already done in our previous lectures. Okay. So, case 1, let the transfer orbit be an ellipse. So, if the transfer orbit is an ellipse, so in that case E will be lying between 0 and 1, okay. And therefore, TAC transfer, this can be written as 2 to the power L to the power 3 by 2, this already we have developed. E cos theta okay. So, utilize the previous results, and if you utilize it, L you can write as L is nothing but A times L you can write as A times 1 minus C square. Okay. So, this will get reduced to A to the power 3 by 2 times 1 minus C square to the power 3 by 2. Zero to theta 0 d theta by 1 plus e cos theta whole square, and if you integrate it, so integration already we have done in the earlier discussion. So, from there we can directly write the results here in terms of eccentric anomaly. Okay. Now, tan E by 2, this we have seen in the earlier derivation in the earlier lectures. This is theta 0. Okay. So, we utilize this result here. So, we will have E minus E sin E to tan inverse, we can get from this place 1 1 minus e by 1 plus c tan theta 0 divided by 2 minus e sin e. Now, here the sin e we need to replace in terms of the theta 0, which is the actually measure of true anomaly. So, sin e can be written as 2 sin e by 2 times cos e by 2 equal to 2 sin e by 2 divided by sec e by 2. What we are trying to do here, convert this sin into cos. So, rather than writing like this, we can write as we have to convert sin into tan. Okay. So, sin e by 2 and we divide it by cos e by 2. So, here it gets multiplied by cos square e by 2. This is a simple trigonometric relationship. So, this is 2 tan e by 2 divided by sec square e by 2 tan square e by 2. Now, we can insert the results from here into this equation. So, we will write this as the equation number R and this is equation number S. Inserting equation R into S. So, sin e then will get reduced to. So, you can do this exercise yourself. This will get reduced to 1 minus e square under root times sin theta 0 divided by 1 plus e cos theta 0. Okay. This is easy checking. So, once we have done this, then our TAC it will become 2 times a to the power 3 by 2 divided by mu under root, and if we look into our equation that we have written, this was the quantity here. So, now we know E, we also know sin E in terms of the true anomaly, and therefore, writing those back into this place, this is 2 tan inverse 1 minus E divided by 1 plus E under root times this we are writing from this place. So, this we can show it in bracket rather tan inverse tan theta 0 by 2 bracket closed. Okay. And this is minus 1 and then obviously E times this quantity. So, E times 1 minus E square times sin theta 0 divided by 1 plus E cos theta 0. Okay, so, this gives you the time of transfer in the elliptic orbit. So, we have assumed that it is elliptic orbit, then this is the result. So, for Now, from TAC is calculated if the transfer orbit is hyperbolic. This implies E is greater than 1. Okay. So, in that case TAC transfer to dt 0 to t 1 by 2 equal to 2 times r square d theta by h, theta equal to 0 to theta 0. Okay. The previous equation basically we are writing here. So, for the hyperbolic orbit you can reduce this. So, earlier we have done it for the Kepler's equation. So, here the way we have developed there you can follow that method for the case of E greater than 1 and you can reduce it to this equation. Okay. See here the difference where it is appearing. Here we have written E times 1 minus E square, because E is here less than 1. Okay. In the case of hyperbolic orbit, E is greater than 1 and this is appearing as E square minus 1. And moreover, here the term was with a negative sign, here it has gone into the with a positive sign, and this time sin theta 0 1 plus E cos theta 0 minus ln, this is the logarithmic base. So, E plus 1 under root plus E minus 1 under root proving this equation can be taken as an exercise. Okay. So, the earlier case, for the elliptic case we have here the A which is appearing, this A can be written as, the A here is r divided by 2 minus r v square by mu, and this we have also derived earlier in our lectures. And for the case of hyperbola, A will be r divided by r v square by mu minus 2. Okay, once we have done this, so here the quantity r v square by 2, we can work it out in the next lecture, because time is getting short. So, here r v square by mu, at least we can write its this expression, how much this will be. This will be 1 plus 2 E cos theta 0 plus E square divided by 1 plus E cos theta 0, and here theta, or the angle AOC, this is equal to 2 theta 0 and r equal to r, which is the radius of the circle. So, this is the radius of the circle. Or radius of the circular orbit, radius of the circular . So, now if the assumed E is correct, then what you will see that TAC transfer this is equal to TBC circular. If it is not, then you need to reassume the you have to reassume the value of the eccentricity. So, the again the steps will be for reassume the value of E for reassumed and known theta 0 is known to us, and assume D, again assume the U E, calculate R B square by mu. Okay. For the assumed value of E, reassumed, what we need to do that here, if this is not matching the TAC and TBC, then you repeat this again. Okay. Once you find that these are matching, then for the assumed value of E and known theta 0, calculate R B square by mu, and then obviously you can calculate A. So, the next step will be calculate A, which is given by equation plus minus 1 by 2 minus R B square by mu. Okay. So, minus sign for hyperbola, plus for ellipse. And obviously, then TAC can be calculated. Okay. So, we will continue in the next lecture, few more steps to be written, but time is getting over. So, let us leave it for the next lecture. Yeah, thank you very much.